Hello everyone, I'm Kosuke Tomonaga. I work for SoftBank Robotics. Today, I'd like to talk about the artificial ego we are developing. The title is What We Achieve with the Artificial Ego in Super Formula. The Super Formula is a Japanese Formula car race that is also the stage for our artificial ego experiment. Now let's begin the presentation. At SC21, we introduced that SX Aura Tsubasa can compute a qubit model based on an extended Riemann sphere. Here, the extended Riemann sphere is a mathematical object we proposed. In the extended Riemann sphere, we consider not only the ordinary Riemann sphere, but also the converse Riemann sphere and inverse Riemann sphere. The ordinary Riemann sphere is the world we live in, and the inverse Riemann sphere and the converse Riemann sphere are the anti-world. The anti-world is a world we don't perceive in our daily lives. And we consider functions travel back and forth between the world and the anti-world through gates that are the poles of the Riemann spheres. The Riemann spheres are connected at the poles. For example, the north pole of the Riemann sphere is connected to the anti-north pole of the converse Riemann sphere, and the anti-south pole of the converse Riemann sphere is connected to the south pole of the Riemann sphere. At the poles, a reversal of polarity and qualities occurs. That is, 0 and infinity are interchanged, and matter becomes wave and wave becomes matter. Using such a qubit based on the extended Riemann sphere, we consider the emergence of information. That is, in the world we live in, functions traveling from the anti-world are emergent from nothing. At ISC 2022, we explained the potential of control engineering with the extended Riemann sphere. In the extended Riemann sphere, we can consider functions beyond infinity and 0. And mu, nothingness, between the south pole and the anti-south pole is a reference of a controlled system. The pole is a point of failure, and we have to avoid such a point to design a system in a traditional control engineering. But we can treat it as a single piece of information in the extended Riemann sphere. The concept we call artificial ego is one of programs that operate in the extended Riemann sphere, and its reference is the center of the extended Riemann sphere, that is mu. We are currently in the process of implementing the initial version of AE in SX Aura Tsubasa. Our artificial ego experiment is taking place in Super Formula's Next 50 project. One of the project goals is to make motorsports more attractive as entertainment. As I mentioned at the ISC 2022, we are not yet at the stage of autonomous control of vehicles, but are working on giving vehicles emotions. In this presentation, we will introduce this experiment of an initial version of an AE. Let's take a look at the AE we ran in our first experiment. Our initial version of artificial ego is installed in a Formula car. The inputs for this AE are the CAN data of the Formula car. Onboard camera will be supported in the future. This CAN data is statistically analyzed to generate driving events. Driving events are states obtained as a result of analyzing driving data. For example, If the engine speed is high for a vehicle, a driving event full RPM is generated. Besides, our artificial ego has a hormonal balance just like a human being. The same input produces different outputs depending on the hormonal balance. The driving data inputs are converted into hormone vectors based on the emotion map. A hormone vector is a vector of hormone secretions. For example, noradrenaline is 1.0, CRH, corticotropin releasing hormone is 0.5, and dopamine is 0.2, and so on. The hormone vector then influences the weight of the links in the neural network that output the emotions. Two examples will be discussed later. The firing cell of the neural network indicates the car emotion. The car emotion is represented by using two types of outputs. One is facial expression, and other is excitement level. The excitement level is the length of the hormone vector, and it means how the neural network is activated. An utterance is then generated from the AE to the driver. The utterance is created from the two pieces of information. One is emotion output by the neural network, and other is driving event. Okay, now let's see how it works.
可能性もある。誰が来るのかわからない。すごい予選です。
もっと速く走りたい。
すごいこのベンツです。
今、
はい。
ピット離れるタイミングが、
この
やはり坪井選手は先ほどと同じ。
This car says, I want to run faster, and I got a good turn, and so on.
スピードが出ています。
出る。
We built this AE for a contest. The contest was held by Toyota's Mobility Foundation, and it asked the question, how can people with disabilities truly enjoy watching races? Our answer was this AE. We are the survivors of the team that developed the emotion generation engine for the humanoid robot Pepper. And AE's emotions are based on Pepper's emotion technology. Many people don't know if 298 km per hour is fast or slow for a racing car. However, if they see the car facial expression and excitement level, they understand that the car is suffering and running hard, then everyone can understand how hard the 298 kilometers is. As a result, people with disabilities gave higher ratings to our AE on the questionnaire, which asked 7 questions on a 10-point scale. As shown in the figure on the left, the average rating for people with disabilities was 8.9, while the average rating for people with disabilities was 9.1. As shown in the figure on the right, at the 7th question, were you uncomfortable with the idea of a machine having emotions? We see that the subjects who saw our AE rated the idea of a vehicle having emotions as not bad. Also look at the 5th and 6th questions. We can see that the expression on the emotion map and the facial expression of the vehicle were also rated highly. In both cases, we can see that people with disabilities tend to rate higher than people without disabilities. Now let me explain how our AE works. The mandala art on the left side is the emotion map. Our AE generates emotions based on the emotion map. This emotion map is the same as the one used to generate emotions for the humanoid robot Pepper. By mapping facial expression to emotions, as shown in the figure on the right, A gets its own facial expression as seen in the previous video. So let's take a look at how to use the emotion map. The emotion map is a graphical representation of the relationship between hormones and emotions. For example, when noradrenaline is secreted, displeasure is more likely to be generated. Displeasure is a negative emotion for survival. Negative emotions are mapped to the lower half of the emotion map. For example, worry, repulsion, fight, and fear are negative emotions. Okay, let's look at another example of a different hormone. For example, when endorphin is secreted, emotions related to willingness are more likely to be generated. Willingness is a positive emotion for prosperity. Positive emotions are mapped to the upper half of the emotion map. For example, joy, love, and grief are positive emotions. Besides, when endorphin is secreted, negative emotions are less likely to be generated. Thus, the emotion map shows the relationship between hormone and emotions. Not only noradrenaline and endorphin, but also the effects of hormones such as enkephalin, oxytocin, dopamine, serotonin, CRH, and LCTH are depicted in the emotion map. So far, we have looked at the relationship between hormones and emotions based on the emotion map. This relationship is implemented in a neural network, where the weights of links changed from moment to moment depending on driving events and hormonal balance. In the neural network, the 4 cells in the center are inputs, and the other cells are outputs corresponding to emotions one by one. For example, if the joy cell fires, it means that the vehicle feels joy. The links in neural network are mapped to 12 directions. These 12 directions are shown in the figure on the right. For example, when noradrenaline is secreted, the weights of the links in direction of 5 to 1 increase. This makes the cell in the lower half of the map more likely to fire. As mentioned earlier, negative emotions are located in the lower half of the emotion map. This means that the weight of the red link in the neural network shown on the left side will increase. Of course, those links are located in the lower half of the neural network. Is 270 km per hour the maximum speed? It depends on the vehicle. Therefore, we statistically process historical data to give meaning to CAN data and organize them as driving events. For example, percentiles can be used to classify speed and RPM and so on. And outliers can be used to determine normality. We also define the hormone vector for each driving event. For example, a high accelerator pedal position means that the exercise starts, so dopamine is secreted. Also, since Formula cars are designed for top speed, endorphin is also secreted. This is how the relationship between driving events and hormones is defined. The values of these hormone vectors are initial values and gradually change. The firing cell of the neural network will tell us which emotion is generated as an output. For example, if the cell fires as shown in the figure, the red cell corresponds to the emotion of furious, so furious is output as the expression of AE. So far, we have talked about car emotions. Here are the results of our experiments of driver emotions. By analyzing the voice of driver, who was communicating with the engineer in the pit. We can get the driver's emotion by data. This is a result of analyzing the voice of driver noisily. If we analyze the voice when he takes the pole position, we can see that he is delighted by data. We can see that he is delighted by data even if we don't understand what he spoke in Japanese. And we also know that the engineer in the pit is tired. Not only was he tired, but the blue emotion in the complex state indicates that the engineer was feeling fatigue. Besides, as I mentioned earlier, we can see that Noziri is very delighted to have broken the record, and they are very excited. In this way, various calculations can be performed based on emotion data objectively. One of the calculations is the synchronization rate. In the Ising model, as shown in the right, the spin matching state is calculated to be positive. In our emotion model, we can calculate the synchronization rate to be positive if the direction of the emotion is consistent. Specifically, as in the unsynchronized state shown at the top of the figure, when the driver is in a state of pressure and the vehicle is in a state of displeasure, we can represent this unsynchronized state by a -1, which is multiplying 1 by -1. Synchronized state, shown at the bottom of the left figure, can be represented by the +1, which is multiplying 1 by 1, if both the driver and the vehicle feels pressure. In this way, we can calculate the synchronization rate of the driver and the vehicle. We can also add data of fans to the synchronization rate calculation. Let's talk about our next goal. As we have talked about, we have the technology to realize car emotion and to detect the emotion of drivers, vehicles, and fans. We also know that we can calculate the synchronization rate of emotions. Therefore, our next goal is to visualize this synchronization rate on a real race. Thank you for your listening.